that you can follow on your laptop, and spend like 10 seconds explaining also this collab. So that if they never use it, the fact that it's hosted by Google and they're using GPUs, they can use it for the exercises and so forth.
Yeah, let me check the GPU. Okay.
Small intro about that.
Hi everyone. Can everyone hear me? Can everyone hear me? Okay. Okay, cool. So this session is just meant to be like a practical session to get you started with using graph neural nets, Pytorch, like general machine learning pipeline, because we recognize that there is quite a bit of variance in terms of people's knowledge in building neural networks or experience with graph neural nets. So this session is just to get everyone on board, know how to do training from scratch, know how to use Pytorch geometric. And then towards the end of the session, we're also going to briefly talk about models that are related to homework. And you guys are welcome to ask me anything regarding the model, regarding the how to use Pytorch, how to use Pytorch geometric, or any questions that you think is relevant to the homework and to graph neural nets. So, the tool that we're going to be using today is mainly the Google Colab. So this is, for those who are not familiar, this is just a Jupyter notebook type of thing where like user sharing is also enabled. So you guys can open this notebook with me, and then you guys can run this notebook on your different Google Cloud servers. So the link is already on the website, and so if you guys want to follow, you can open the link. Just follow the steps that I'm going through. Yes, please. Oh, yeah. Maybe I'll do like oh, probably because Andrew is building this, so. Yeah. Sorry. Oh, because Andrew created the file, and then I was editing on his file, so probably that's why. Okay. Does everybody get the permission? Okay, cool. Cool. So for the first part, I'll just give a brief introduction on how to use Pytorch or like some Python basics to build machine learning pipelines. So we'll start with a very simple example, say MNIST classification that everyone in machine learning should be familiar with. So the package that we're going to be using is mainly like those Pytorch packages. So torch.nn, which we abbreviated as nn, torch.nn.functional, which we abbreviated as f. So nn has a lot of modules on neural networks, and functional has a lot of function definitions that's related to neural network operations. These two are just specific for MNIST, which you don't have to care. And then the last one is the metrics which we use to perform evaluations of the model. So I've already ran this because so here in the second part, this is just loading the data set. So this is going to take a little bit. So I just ran it before I came. But I guess the thing that you have to know here is that before you start training, you have to get a sense of the concept of data set. So this is like the data structure that Pytorch keeps for you to get input for the model. So these are storing all the data set. In this case, this is the MNIST data set. And for later on, we're going to use, say, CiteSeer, Enzyme, IMDb, these other kind of graph data sets, but all in the format of this Pytorch data set object. And so here, this is where we define the training set. This is the loader that loads the training set. So what this Pytorch data set is really is, it's just inheriting from some abstract data set format that is an iterable. So the main functions that you want to inherit when you build your own data set is the thing called len, which is the length of the iterable, and also the index. Like you'll be able to index into specific examples into the data set. For example, maybe I can show here. So this train set thing. Oops. So this train set is just this thing here, which is a Pytorch data set. Oh, it's gonna take a bit, but you can also do something that's very common to any iterable, Python iterable, which is like you can print the length of the iterable, and you can print, say, what's the first example, like any index that you can put in. So this basically retrieves you the 10th example of the thing. It's still running. Why is this so slow? Were you able to download the data set? Okay, cool. And you should be getting some results. Okay, but this is what you have to do for iterating over the data set. So you can index into a data set to retrieve one example from the training set. But in practice, what we do is mini batch training, right? We do stochastic gradient descent, which means that at every iteration or at every iteration, you take in multiple examples. So this is also the way like you take multiple examples. You can take like say 10, 11, 12, or like after shuffling or something like that. So yes, so this is the basic concept of data set, and as you can see, like it will print out the number of data set. This was actually the previous run, so it printed out the data set itself. But like now I'm printing out the length of the training set, and I can also print out like the specific data example that's here. So basically, this array is just an image array of 26 by 26, which represents the MNIST digit. Right. So once you constructed the maybe you can just yes. So once you constructed the data set, now it's the time to construct the model. And so we will do like this. We first construct data set, we then build our model, and then we link the model and the data set together to do training and testing. So here it's a very brief or very simple example of like MLP with one layer convolution. This is like really simple model just to demonstrate how would use Pytorch to build this kind of network. Just show of hands, how many people are familiar with like Pytorch concepts? Okay, like half of it. Okay, so maybe I'll explain a bit more in detail. So every model every model that you build in Pytorch is inheriting from something called like NN.module, which is like a superclass of any neural network module. So this provides a lot of good things that you will later see. Like it provides easy interface to optimize, easy interface to run inference and training on that model. So this module mainly has like two functions that you have to implement. One is initialization, and one is the forward function. So the initialization basically helps you to define all the parameters that you use in the model. So these are the places where you put in all the trainable parameters, and later on you can retrieve these parameters in your optimizer and optimize for these parameters, right? And the second part is the forward function. So what the forward function does is it basically tells you how to construct the computation graph from the input to the output, right? In this case, the parameters that we care here is just the convolution, 2D convolution, which you don't need in graph neural nets, but and then the second one is the linear layer. The third one is also a linear layer. So these are all the parameters that we use to train this model. And here we're defining, so linear layer has two inputs, the input channel and the output channel. So these are pretty useful because we will see a lot of linear layers in graph neural nets. So here, the input is something like 26 by 26, which is the size of the image, and then 32 is the number of channels, because we noticed that the number of output channels is 32. So here, this is the input dimension, and this is the output dimension. I have a hidden layer of 128 neurons, and in the second convolution, I take in this number of output here, and then I output 10. I output 10 because this is a classification task, right? So this is classifying which digit is the MNIST number is. So the number of possible digit is 0 to 9. So this is like a 10 class classification task. Right? And in the forward function, this is what we do. We take an input x. So the forward function takes in the input of the actual tensor, and then it builds the computation graph here. So the notion of computation graph actually starts from TensorFlow. But the good thing about Pytorch, which also makes it easier, is that you don't have to pre-construct your entire computation graph before feeding in all your data. So you can actually on the fly retrieve your data from your computation graph, look at it, maybe even modify it, and then feed it back into your computation graph. So it's dynamic. Yes. Sure. Again, it's not going to be important for this class, but the shape for the convolution has 3 parameters. One is kernel size, which is the filter size, the filter dimensions, which is 3 by 3 in this case. And the input channel is 1 because this is a black and white image, so just like a grayscale. So input channel is 1 because it's 1 dimension. And output channel is 32. It's just like the conv output channel for the, yeah. But it's not going to be used for graph neural nets. It's just there for image classification. Yeah. Yes.
Why is 32 plus 1 plus 1 in the forward function?
I'm sorry?
In the forward function, the first comment about the shapes of the...
In the first forward function.
X is the batch or the single?
Yes. So there's a batch dimension here. So the 32 in this case is the batch size. Yeah. Yeah, again, this is variable. So there's also a flatten here, which means that you flatten this multi-dimensional array to 1 dimension. This can also be very useful in graph neural nets, by the way. And this is not the only way. So this way, this is actually the flatten is actually an operation that connects the input tensor, which is this x, to a different tensor, which is also assigned to x. So you first do the computation on x, and then you put the resulting value back to x, right? But this could be a little bit expensive. What we usually also be able to do is we can use this view function like this one. I think so the tensor.view, and we just specify because we want to flatten it to 32 by whatever the rest of the dimensions, so just -1 here. So this essentially does the same thing with flatten. But the good thing about this is that it doesn't actually does the actual computation of changing the shape of the x. It's just providing a different view of this tensor. So a different view means I look at it differently, but it's in the same memory, So it's a little bit more efficient, but computationally they are equivalent. These two are equivalent. Yeah. By the way, you can look at the documentation of the view in the Pytorch tensor documentation. But so after this computation, we do nonlinearity, and we produce a logit. Logit is essentially the 10 class here. The output is dimension 10. So 10 class, we pass through a softmax on the logits, which the logit is the 10 class score. So for those of you who are not familiar with softmax, it's just a way to differentiably differentiate kind of max, right? So say I provide a score for each of the candidate class, and I use this particular function, e to the power of ci over sum of e to the power of c j for j equals to 1 to n. Right. So so this will be the probability of the model choosing that particular class. Right? This is just basic softmax. And then with this softmax, we can use like cross entropy to compute the actual loss. Right? Is the basics about Pytorch clear? Is there any questions on Pytorch? Okay, cool. So once we define the model, we can actually start working on actually running this model. Right? So maybe let's first start with a very simple example where we don't actually train the model, but just like to look at like what these tensors are. Like for example, we can define A equals to is numpy. So we can say define A equals to some kind of tensor. Right. So this is not a tensor. This is a numpy array. NumPy is not defined. So this is a NumPy array. Everyone is familiar with NumPy array, right? And we can define something like np.once. We can do like similar things, right? This is just a 2x2 matrix of ones, right? And if you print B, it will be a 2x2 matrix of ones, right? And in NumPy, we can do operations like matmul, right? You can do matrix multiplication between these two. So you can do np.matmul AB. So this will give you the matrix multiplication between matrix A and matrix B, which turns out to be this. But this is in NumPy, and which is also just using CPU for your computer. But the good thing about Pytorch is that you can do this linear computation in like GPU. So you notice that like here our runtime type is set to GPU here, so which means that we have a GPU available. So we can do this using Pytorch on GPU. So what we do here is that we can define this thing called tensor, which is the object, like Pytorch object that they use to perform the computation. Maybe tensor A is something like torch.tensor, and then you put in this NumPy array. So it will. So if you print the TA now, this is going to be a Pytorch tensor which is wrapped around the NumPy array, right? You can also define a data type, float, right? So now it tells you this is using float 64, right? And we can do the same thing for another. And so here we can do either torch.tensor B, but we can also do like torch.once. So you notice a lot of similarity between calling NumPy function and calling the Pytorch function. So is it this one? So now we print TB. All right. So and we can also define D type similarly float. This is all very similar to the NumPy interface, so it's very easy to use. And now you can perform computation using torch functions, right? So now instead of calling the numpy.matmul, I can do torch.matmul, right? So TATB. So this will give you matrix multiplication using Pytorch, right? Or just as like a very simple shortcut is just do this, which also gives you the matrix multiplication, right? But here, all the tensors still live in CPU because we just tell the Pytorch to construct this tensor, but it's still in CPU. So the way that you do GPU is that you can look at what the GPU is available. So torch CUDA is available. This will give you true. So now, because our runtime, as you noticed, is GPU, so it says CUDA is available. And because it's available, we can now do something like transferring the data into GPU. And the way you do it is the very simple way is this. You just let the torch put it to any GPU that you can specify. So now, if you print this thing called TA, whatever, it will give you something in the GPU, right? Okay, yeah, the first time transferring data is a bit slow, but you notice that there's like a device device thing that wasn't there before. So now this means that it's in GPU, right? But a lot of times that you want to make sure specific like which GPU you want to actually use. So this time you want to call to device. So so device is something like essentially this string there. So in this case, we only get one GPU. So this is the GPU that we are using. So so it's like that, right? So but it's equivalent. It gives you the same result. So is there any question on like GPU, using GPU, Pytorch tensor stuff? Okay, great. So it's easy. Okay. So yeah, so here it's the same thing. Here we just define if the CUDA is available, we set it to CUDA 0. Otherwise, we use CPU as the device. Right. Now we use the tool call that I used before to get to the device, and this is how we construct the model. And then we define the loss. So this is the loss that we use to compute the difference between our trained softmax versus the ground truth label, which is like 1 digit out of 10 digits, right? And then this is the optimizer. So a lot of optimizers are there. So you can look at the torch.optim. Whatever. Like there are a bunch of things like SGD, RSGD, AdaGrad, AdaDelta, a bunch of those, and you can try whether these fit you. And there's one thing that's worth looking at, because a lot of times you want the learning rate to be kind of annealing over time, right? Initially, because the model is not very trained very well, you want the learning rate to be big, so you can like step with big steps, and then later on you want the learning rate to be decaying or like annealing. So there's an option called schedule in the optimization package. So there's like different kind of annealing operations that you can do. There's like step annealing, there's like linear annealing, there's exponential annealing. There's also something interesting called cosine annealing, which people in vision likes. So so yes, so you're encouraged to look at this, but it's not strictly necessary, but it could improve your performance. So once you run this, I probably have already run it, then you can start the training. So we have everything ready. We have the model ready. We have the data set ready. We have the optimizer ready. We have the loss ready. So now we can do the training. So the training loop essentially goes like this. So there's a fixed number of epochs that we need to go through. Typically, like this just represents like the number of times you need to go through the entire data set, right? We also recording the loss and stuff. And then, okay, so here is for each of the epoch where you go through the entire set of data. Now we enumerate over the data loader, right? Remember that data loader is a wrapper around the data set, which you can index into. So this enumeration here just tells you like at every iteration you want to extract the number of examples equal to your batch size. By the way, batch size is also defined in the loader. So now for every iteration, this is the thing that is retrieved from the data set. Remember the train set, I said train set 10. So this is the thing that's in the train set 10. So here, in this case, is image and label, right? So we put everything into GPU. We perform the model. So when you see like the model and then parentheses, the input, this means that this is calling the input function, calling the forward function of the model. So this is the function that it calls, right? So the input here is x, which is the image, and that's why we put the image into the model, right? Once you do that, there's an important, the loss is, of course, the loss is the cross entropy loss, which you can look up. It's a very standard cross entropy. But here there's an important step that you really need to do, which is zero grad. Zero grad basically sets the gradient to 0 for all the variables. This is very important because if you don't do this by default, the Pytorch is gonna accumulate your gradient, right? Say like you have already computed your gradient for all your parameters in your previous iteration. If you don't do zero grad, it's gonna add back the gradient of the current computation. So it's gonna be a sum of your previous gradient plus the current gradient. And this is not what you want in a lot of times. So you really need to call zero grad if you want this kind of behavior. Yeah. So this is a function where we compute gradient. So backward means backprop. So backprop computes all the gradients for you for all the parameters that you define. So if you don't forgot where the parameters are, these are the parameters, right? For linear, the parameter is the weight and the bias. So the weight will equal to this. The number of elements in weight is equal to the input times the output, and the number of elements in the bias term is the number of output, right? So these are the parameters, and when we call backward, all the gradients of these parameters are computed. And now we do optimizer.step. So when we call optimizer.step, we're saying for all these parameters where we already have gradient, we want to perform one-step optimization with the learning rate that's specified here, right? So and also, okay, maybe I'll also explain the parameters function call. So this is just so it's perfectly fine if you put a list of parameters there, but this model.parameters is just a abbreviation to help you. So say like I want to optimize all the parameters that is defined in init. So this is what you do, right? You just call parameters, and then it will help you. So it's essentially giving you all the parameters here. And how do you decide? Is there anyone has a clue? How do you decide whether a parameter here is included in model.parameters? Is there, like, say, for example, if I do something like this, say x equals to nn dot linear 5, 5. Is x optimized? Is x included in model.parameter? No. Yes. Good. So, is anyone know why it's not included? It's a very tricky thing. So okay. So the reason that x is not included here is that I didn't add self. If I do this, this is in the parameters. It's in model.parameters. This is just like a very specific thing about nn.module. Like you have to define this self for the model to for the parameters to be included in the optimizer so that you can optimize. And there's also a caveat. Like say I want to have like a list of parameters I want to optimize. Say I have a 3-layer neural network. Say I have this for I in range 3. Oh, range 4, whatever. So if I have this, anyone know why? Anyone know if this is included in the parameter list? So this will also not be included in the parameter list, even if you have self, but because this is a list, so it's not being included. So what you do instead is do nn.module list, and then you put the list there. In which case, it will be in the model.parameters, and you can optimize that. Yeah, just like whenever, like sometimes you don't see the loss coming down, or you don't see the parameter changing, it could just be because that the parameters are not actually in your model.parameter list, so you didn't actually optimize that. So it's good if you know this and know how to debug those. Right? Make sure that your list of parameters is the list of things that you want to optimize. Right. Okay, so now we can perform training. So this is essentially the entire training loop that I just explained. I explained onto this step, which is optimization of optimizer.step, and there's also accumulating the loss. But these are very simple Python stuff. Right. And note that this is the label. So I will talk about it later on the evaluation metric. I will explain what this is. But just to get a sense, this is like how you train neural nets, like going through a lot of epochs. So here I'm recording the epoch 0, which is here. But there's we can go through the data multiple times to get results. Right. So okay, so let's talk about testing. So I assume that you guys know basic concepts about like test sets, training set, right? The basic idea is that you want to evaluate how good our model is, but you don't want to use your training set to evaluate it, right? Because you only train on this, so there's a possibility that you overfit on the training set, but the model doesn't generalize to data that you have not seen before. So this is how you do the test set. So the thing about tests is that the evaluation metric does not have to be differentiable, right? Your training loss has to be differentiable because then you can do SGD, but your test metric need not be differentiable. And these are typically things like precision, recall, F1, things like that. Is there any question Okay, cool. Okay, this is just training. I can kill this. It's not important. Okay, but you will see like loss sort of going down and all that. So in the test, we basically want to evaluate how good it is. So what we do is we take a different set of data in the data set. So here, see the test loader. So test loader is constructed from the test set, not the training set. So you notice from the previous code section that these are two different data sets. But the idea is the same. We enumerate over the entire test set. And for the images, we go to GPU. For labels, we go to GPU. And we produce our model output. And remember that the model output is this thing, right? It's the softmax that we kind of computed from the model set from the model class. And okay, so this is maybe I need to decompose this. So so this is essentially the model output, and then out of all the scores that we computed this way, we want to pick the maximum of these to be our class, right? So say like the model predicts 0 with possibility 0.5, 0.1. 1 with possibility 0.1, but 2 with possibility 0.8, right? So you would say like the model actually thinks that the digit is 2, right? So in which case we are picking the argmax. So essentially you can treat this as your predictions. So torch.argmax, which tells you the maximum is, outputs 1, right? And of course you can flatten for sure. So this is your predictions, and this is your labels, right? So we can print both. We can print labels. We can also print predictions, and we just run it for one iteration. So just to let you know like what this looks like. So this is our prediction. The model predicts 7. The label is actually 7. It's all correct, right? No, well, it's all correct. Okay. So, but we want to evaluate it based on these model outputs and the labels, right? So what we want to do here is that we can make use of the remember the library that I just like I mentioned at the beginning. So there's like this sklearn matrix, which helps you, which already defines a lot of metric function that you can use. For example, accuracy, for example, precision, etc. So. So here we are computing accuracy ourselves using min and items, but we don't have to do that. We can just make use of the sklearn. But the thing is, sklearn is implemented based on NumPy, so you have to convert this thing back to NumPy. And the way you convert this thing back to NumPy is you call CPU, because this thing is in GPU right now, remember? And also you need to compute the NumPy, so convert to NumPy. Is that clear? And I can do same thing for the labels, labels.cpu, just convert back to NumPy, right? And then I can make use of my favorite sklearn dot metric. I have already say there's a lot of different functions in it. So almost all the evaluation methods that you can think of is already implemented. So you can basically call a lot of different things. For example, precision. Remember, precision is true positive over what? True positive plus true negative. No, true positive plus false positive. Yes, true positive plus false positive. So, so this is how you compute the precision score. You can print the precision. So I'm just going to run for one iteration. Oh. So here this is a multi-class classification, but by default average is binary, which is only for binary classification. So in which case you want to do, what's it called? Average micro, say you do micro average of 10 class, right? Yeah, I guess don't care about this. So now precision is 1, but then you can do different other things, right? Recall, and there's PR curve, there's everything. Like you can do it this way. But okay, so let's remove these just to let you know that you can use sklearn to perform all these evaluations. And in this case, it's doing test accuracy, which means that so. Right now, just now, I printed the precision recall for one iteration. Now here, I need to aggregate over all the iterations of the data set, so to get the overall accuracy, which happens to be 0.99. So yeah, so that's the basic. That's all for the basic tutorial for the Pytorch. Is there any questions on Pytorch related training with ML models? Is everyone following? Yes.
How did the loss get taken into account in the training?
How did
because how are loss and your variables loss and optimizer linked together?
Oh, the question is how is the loss and optimizer linked together? So they don't link together directly. So what you see here is that you compute gradient of the loss. So when we say loss.backward, it computes gradients of all the parameters in the model, right? This is the signal from the loss function. So once you get the gradient for all the parameters, then optimizer here only cares about parameters. So you realize that optimizer takes in the set of all the parameters, right? And all the parameters have already been computed the gradient. So so once you call optimizer step, it just take all the parameters, look at their gradient, and it performs one-step optimization. Is that clear?
But loss is constructed from criterion, which is separate from your optimizer.
Yes, exactly. That's the point. So the loss is not directly related to optimizer. Loss is related to your gradients. So loss tells you the gradient of all the parameters. And then based on all the gradient you compute, your optimizer comes in, look at the gradient, and perform one-step optimization based on these gradients. So the loss and optimizer themselves do not call each other.
I'll find you after.
Okay. Okay. Yeah. The general idea is that you compute gradient for all the parameters, and then you perform optimizers based on these gradients. So you don't have to look at the loss to compute your compute your step, because you already know all the gradients of your parameters. Okay. So we'll then cover the Pytorch geometric. So before covering the Pytorch geometric, I'll just say like this is just one library that we can use. We think is like easy to use, but it's not like the thing that you have to follow. There are a bunch of libraries like GraphNets from Google if you're interested in TensorFlow, and there's also DGL, which is from Amazon, that supports both Pytorch and MXNet. So there are different kind of frameworks that you can use, and this is just like one way to like as an example of how to do this. But you can, if you want, you can also implement it from scratch. It's actually not that hard as you would think, because I think in your slides there's also like one slide about how to do the computation, which essentially says like you just do the matrix multiplication of your adjacency, of your weight function, of your feature matrix. You can do this matrix multiplication in Pytorch, so you can even write it from scratch. It's not that hard. But this is just a way to like help you provide additional utilities for you to write it. So I already installed the libraries here. And these are the set of dependencies that we would need for the Pytorch model, Pytorch geometric model. So let me just briefly explain. You already seen this, and here these two are specific to Pytorch geometric. So this NN module here is the neural network module that's specific to Pytorch geometric. So it implements a lot of things like GraphConf, GeneConf, and like different kind of graph convolution models. And the util here is basically perform some graph utilities functions. So we also use NetworkX to just visualize the graph. It's not important and it's not necessary. Optimizers. So these are the data sets that we would use. So this the good thing is that a lot of standard graph data sets are already like easily ported to these libraries, so you can just download them automatically from Pytorch Geometric. But if you have custom data sets, it's also easy to build them, like as I showed in the Pytorch dataset function. Okay, and here are a bunch of things that helps you to perform visualizations. So I like TensorBoard X. So this is basically an interface between Pytorch and TensorBoard. For those of you who have not used TensorBoard, this is just a way to track your training, like how well you perform over time. Like you can see, like plot a graph of loss with respect to the number of epochs, or like metric like accuracy with number of epochs and so on. So it's very easy to track those during your training, and I'll show how to do this. And this is for t-SNE visualization, so you want to embed the learn embedding into like a two-dimension thing that's easy to visualize. This is how this is one way to do it. And finally, this is just a plot, matplotlib plot function. Okay, so let's start with the how to write the general model for GraphConv, assuming that you already built a or use a built-in convolution operation that Pytorch Geometry already defined. Right. So this is just a stack of graph convolution. It's like very simple model here. And as you already know from the previous example, that this is a model, so it inherits from the nn.module. The torch here is not actually necessary, I think. So because I already named. So it's inheriting from nn.module. So there is like the initializer, which you have to implement, and there is also like the forward, which you have to implement. So it's the same. But there's a few more things that you have to put in here. For example, here I was using the module list, which I talked about before. So here you put in all your convolution operations. So here I'm putting in a convolution model that takes in the number of input dimensions and number of output dimensions. And I'm also building two additional layers of convolution here, right here. So this is going from hidden to hidden, right? The hidden dimension, the input is hidden dimension, the output is also hidden dimension. And we can look at the build conv. It's really very simple. I'm just saying, like, if it's like a node classification, I'm using the most simple GC conv, the graph convolutional networks. And here, if it's a graph convolution, I'm using a particular model called Gene for graph model, but we'll look at how to implement this later. So you can even like input your custom conv function, and this is actually the function that we are asking you to implement in the homework, right? The class that is subclass from the message passing superclass. Okay. So here. Here, after the convolution, I also have additional parameters here, like a sequential. Sequential here is very similar to module list. So we define a list of these layers. And the difference here is that if we call sequential, that means we execute all these layers sequentially, whereas in module list, you can execute out of order or in whichever way that you like. So this sequential always executes sequentially. So you perform this first linear layer and then drop out, and then second linear layer, right? Okay, is there a question on the model? Okay, good. So we talk about the forward function, but this forward function is kind of specific to graph neural networks, right? So this forward function takes in the data, which is your input. So this data is an element of the data set. Remember the Pytorch data set that I talked about. You can index into every element of the data set to get an object here called data. So the data here consists of X, which is the feature matrix. The dimension is number of nodes times the number of nodes embedding dimensions, right? Or node feature dimensions. And there's also edge index. You can see edge index as like an adjacency matrix, sparse adjacency list. Basically it says like what are the edges in your graph. So if there's an edge between node 1 and node 2, here there is the first row is 1, 2, right? And 3, 4, 1, 3. So this is an adjacency list of the graph. And here is the batch. The batch is a little bit complicated because now we need to, so instead of batching images, which is like regular, having the same number of nodes, now we need to batch graphs. So as we all know, graphs have different number of nodes. So if we want to batch a lot of graphs together, especially in graph classification, then we want to know which node actually belongs to which graph. So this is telling you like which node belongs to which graph. So internally, it's an array that says like which node for every element of the array, you record which graph it belongs to. So in practice, you see something like 1, 1, 1, 1, 1, which means there are 5 nodes that belongs to graph 1, and then followed by, say, 2, 2, 2, which means there are 3 nodes in graph 2, and so on. So this is a batch of some number of graphs. And if it's node classification, as we will see here, so there are a lot of node classification that only runs on one graph. So in which case, the batch here is like all ones. So it's like a trivial kind of graph. So here we have just a sanity check that if there's no features, we use constant feature. We also talked about it in class. And here we have a number of layers that execute the convolution. So here, convs I, remember this convs is a module list here. So this is a module list, which has a list of these elements. For every element is a layer, right? It's a convolution layer. So for I in these many layers, for every layer, I'm performing one different convolution here. And then pass through a value and drop out, right? So one thing about dropout is that there is also this training flag here, which you might want to take a look, because dropout computation is different for training and testing. As you all know, like at test time, you cannot, you have to rescale the value. So that's because, right? It's because at training time you drop out, so the magnitude of all the outputs is kind of larger. So at the test time, you kind of want to downweight that. So you have to specify whether you are in training or not, so that the dropout knows how do you compute this. So at test time, it just passes through everything. At training time, it will drop out, right? And lastly, we said if this is a graph, if this is a graph task. So here I just mean like you are doing graph classification rather than node classification. You need to do a pooling mechanism, which we also discussed. So you need to pool all the node in. Oh yes, please.
So in the previous part, sorry for interrupting. In the previous part, you had PyGENN.GCN convolution. That creates a convolutional layer.
Yes.
Right. Okay, and then just specify the parameters to like kind of specify how big the layer is.
Yes. Yes.
Okay.
So yes. So the question is here we have this PyGNN .GCN conv. So this defines one layer of convolution, and we are now simply stacking together a bunch of these layers as shown here. We have a for loop that stacks all these layers, and every layer here has its own parameters. So these parameters will be internally defined in this GCconv function, GCconv module class that I will explain later. So the parameters are not directly defined in this model, but defined inside these convolution layers of individual layers. Okay. Yes. Just to continue, if this is a graph classification, we need to do pooling. This is one way to pool. We can do min pool, and I think the homework does max pool, but doesn't matter. Different kinds of pooling mechanisms that you can also call. So you can also refer to the package to understand like what kind of pooling mechanisms are there. And in general, it's also an interesting research topic of like how do you actually pull all the nodes together into one graph embedding. So here, global min pool just means I'm taking average of all the node embeddings. Oh, and here is the post-MP. Remember, the post-MP is defined by this sequential MLP here. And that's it. And log softmax is, again, doing this softmax with log so that you can do cross-entropy. I'm also returning embedding here because I want to later visualize what the graph looks like, or what the embedding is learned to be. So I'm just returning embedding also. And for the loss, because now we computed log softmax, we just need to do the negative log likelihood of the predicted log softmax with respect to the true label distribution, which is a one-hot distribution of the label class. So as you can see, this is for node classification and graph classification, and this is the general model that is also like very similar to your homework. Of course, in homework, I was asking to like implement a few more details, and then also in graph stage we have like specific convolution models. But this is the general homework. Okay, so now we talk about like what is GCN conv and gene conv really is. So, these convolutions are like a concept defined by Pytorch geometric. So this is the class. So all these gene conv and GCN conv inherits from this message passing class. Have I already run this? Okay. So here we're saying like maybe we come up with our own convolution module. Maybe we have like special needs that we want to do, or like we have special ideas we want to implement, so we don't want to follow the standard GCN conv. So here is how you implement the custom convolution layers. So our custom convolution layers is also inheriting from message passing, and note that the aggregation here, when we call our superclass, we define the aggregation function here. So here we just add all the messages together. So that's add, and we can also take min, max, and all these here. So, but we do add here. So yes, the previous students was asking the parameters, where are they defined? So here is where it is defined. So here we have a linear layer, like the parameters in the linear layer that's defined for that specific convolution. And as usual, because this nn.message passing is a subclass of nn.module in Pytorch, we also implement both the init and forward function. It's all the same, right? It's like module inside a module inside a module. So in this forward function, because this is graph neural nets, we have two things that we want to use as input. One is the connectivity, which is the adjacency list in the edge index, and one is the feature matrix, which is X here. And I also have the shapes listed here. The n is number of nodes. This is the number of input dimensions. Edge is number of, so 2 here just means like every edge you have 2 nodes, right? You want to specify the 2 nodes, and here is number of edges here. Did something like add self loop. This is just means that because in GCN we do something like this, right? We do something like the apply to a nonlinearity feature matrix and so on, right? So here, yeah. So here the edge, the self loop basically means that my A is different. So I also want to add myself into your convolution. So you not only aggregate neighbors, you also like add your self. This just means that your A is actually like not actually your A, but this is actually A plus your self loop kind of thing. And that is implementing that, but we can change it a little bit also. So for example, like there's a lot of customization that can be done here, right? You don't have to add self loop, and there's actually like a remove self loop over here. So you like make sure you don't do self edges. And the reason we don't do self edges is that then we can do like a skip layer on top of that. So what we do is, okay, so I have like say, I transform my edge, I transform my x-axis, and then I do the propagation. So this propagation, what this does is it's calling the message function, so it computes the messages for all the nodes, and then does the aggregation to get the new representation based on your neighborhood defined by the edge list. But then I can do a skip connection here, which means that I can define, say, another linear layer for, say, lane self. So I just defined another linear layer, and then I want your self embedding to be passing through that linear layer, and then I want the rest, the messages to pass through this linear layer. So what we do is here, instead of passing in the message itself, I pass in the linear layer here, like that. So we don't need this. And this is how we propagate all your neighbor information. And what you can do is you can also add your self information, which is what we just computed here, right? Is that clear? Like I add myself, and then I add all the neighborhood messages that we aggregate from the propagate function. So the propagate function is propagating all your neighborhood information, and the thing that we are propagating is this, like x passed through a linear layer. Yes, please. Yes.
So here the aggregation sort of happens behind the scenes. We don't have to manually tell it to aggregate.
Exactly. Yes. So the edge list is telling it how to aggregate. So it's using the edge list to define the neighborhood of the node where you want to pass messages. So you don't have to write the so essentially this package is helping you to do that. That's the only thing that is helpful. Yeah. So here messages it's just computing message. I note that a lot of things here and here you can like kind of switch places. It's not like but it's just that, so the message function is called inside propagate. So, yes.
What does super mean? Like when you put super as a constructor, what does it do in fact?
The question is, what is super here?
Yeah.
Super here means that I'm calling the super class of the current class. So here we see custom conf is inheriting from nn.message passing, which is inheriting from nn.module. So when I call super here, I'm calling the constructor or the initialization function of the message passing class.
Okay, it will not work if we have done a custom on point init. Without super, it will not work.
It will not work. Then you're calling yourself. Yeah. Yes, you have to call super. And it's best to call it before everything in your init, because then you get all the, like Pytorch and then module is initialized first before you define everything. And here I'm doing a lot of computation here just because I want to do this thing. So this is the GCN conf. I'm essentially reproducing the GCN conf, but you don't have to do this. Like if you just want to add all your neighbors, because there's a paper that shows that adding like aggregation by adding all your neighbors is best for graph classification. You don't actually need all these, right? You just use yourself as messages. And alternatively, you can like put this thing here. It's all the same thing. And also there's also another thing that, so in the message can take in everything that propagate takes. So these two has the same signature. So message can not only take the xj, which is your neighborhood neighbor embedding, but it can also take xi. Xi is your self embedding. So your message doesn't have to be like a function of xj only. It can also be a function of xi. You can write something like xi minus n. It's probably not going to work well, but like you can define a complex module as a function of xi and xj here as your messages. Update here just means that after you do the message passing, after you compute the node embedding, do you have additional layers on top of that to further transform this? For instance, I think in GraphSage, what we do is I did like a normalized embedding. So I think it's like something like this. Do L2 normalization with the last dimension of the something like, but I'm not. Yeah, you can do a normalization. You can do MLP or like anything that's after message passing. Okay. Let's check if the. Yeah, I think that's it. So here the story is that you. Once you write this kind of message passing subclass, you can essentially replace this with the message passing. So let's try. Yeah. So essentially, instead of saying, where is it? Instead of saying like paygnn.gcnconf, I can change it to our custom conf, right? So then you can run your method. Yeah, but yeah. Oh yes.
specify how far the messages will go, like the like the depth of your genome?
Yeah, the question is how do you specify the depth of your model? So there, so this is in the GNN stack. You remember the module list where I put all the confs? So this essentially does 3 layers, right? I put in one conf from input to a hidden. I put a second conf on from hidden to hidden, and then this is a loop over 2 layers. So essentially in the forward function, there's also a loop here. So I take the input, I try to use the convolution that I just defined. I get the output, and the output is fed back in this loop, right, as input of x. So that's the layer.
That is the depth of the network model, but that because we saw in class that there could also be a depth of the neighborhood, so like the k-ops. So where does this happen?
Yes. So the question is, I guess, where is the where do we so the yes so this is still by looking at these few lines. This model list does these 3 hops. So this is the depth in terms of what Yuri said, like the depth, how far you want to fan out. It's not the depth of your neural network layer, because every one of these can have multiple layers. And so this is the number of hops you want to go away. So here in the forward, because we have the loop over 3 layers, so for every time you take your input, you perform your convolution at that layer, and then you get your output, right? And the output is fed back into the input as the input of the next layer. It's just a for loop to go over multiple hops. Yeah.
Post message passing.
Oh yeah. This one. So because in practice in graph classification, oftentimes it's beneficial if you have a few more linear, like few more layers after you finish the message passing. So this is just like if you look at the post message passing, this is nn.sequential, as I explained. nn sequential does like every of these layers sequentially. So it performs 2-layer MLP on top of your graph embedding that you just computed. Again, it's not necessary, it's just something we added. So it's just to show that we can customize the model with different architectures. So yeah. Let's show the training loop here. Yeah, the training loop is very similar to the previous one. So in the sense that we built this data loader, and these code are already written for you in the homework, so you can also look at the homework. The thing to note is that we have this train loader, which loads the data set from the first 80% of the data, and then the test loader is from the 80% to so the rest of the 20% of data. So in practice, you have to note that there's also like train validation and test split, right? As you all know, test split is something that you don't want to look at. You look at the validation split at training time, you evaluate the performance on validation, and then you can perform some kind of early stopping. You see the validation curve goes like your accuracy increases, but then decreases. You want to make sure like you stop at the, like do some early stopping. And then once you determine the best epoch where your model performs, like the epoch that your model performs best, you can use that model to perform on your test set. So test set is like one time thing that you don't look at before you training, before you finish training. Right. So, but here for simplicity, I'm just doing this train and test split. But note that like in proper thing, like you have to do train, say from everything to 0.8, and then validate on 0.8 to 0.9, and then you test from 0.9 to 1. So you have a different test split. And specify batch size by 64. I also shuffle the data so that I can have different ordering of the mini batches. Here is the same. I construct the model. It's very similar to the MNIST framework. Construct the model, construct the optimizer. Note that I still call all the parameters. So the optimizer is optimizing all the parameters of your model. And then I start the training loop. The training loop starts with like 200 epochs, and I just, for every epoch, it's the same. Like I get the mini batch from the loader, 0 grad, super important. Get the prediction, if this is a node classification, I also have this mask. So just to clarify this mask thing, because in node classification, a lot of times we have one graph. And in this one graph, we want to do train test split, right? You want to train on nodes, a subset of nodes in that graph, and test on some other nodes that you have not seen before. So this masking is saying like you can have a look at those nodes that are not masked out. So these are your training set, and you mask out all the validation and test set. So this is what this mask is doing. And this mask is also like is defined in the data loader. So it's also in your homework, which you can have a look. And at test time, your mask is instead your validation mask or your test mask. So this is a way, like this is how we train on a single graph with different train validation and test nodes in the same graph. But if this is not a node classification, if this is a graph classification, typically there are a lot of graphs, right? So we just split by graphs. So your train set is, say, graph 1 to graph 10. Validation is graph 10, graph 11 to graph 13, and so on. And now we just compute the loss. So here the loss is added to the total loss, and we monitor the loss. So note that the add scalar here. So this is from the writer. So I will explain that later. So this is a very good like TensorBoard stuff. So instead of looking at the loss as we just did in MNIST, like printing out every entries, it is also very convenient if you can if you write out in TensorBoard. So this is doing this. So I'm writing this loss with this total loss value and then the epoch. So it will help you plot the graph of the loss. And this is testing. So testing does. It's also very similar, but except the train mask, I'm using a validation mask for node classification, and I'm checking whether the label is equal to the prediction. Yeah, it's very similar. Like you loop over all the data, all the mini batches in the data loader. But here, note that this is a little bit faster. You don't have to add this, but if you set with touch the node grad, you will not compute any gradients. So that will make it slightly faster because at test time you don't optimize, so you don't have to compute gradients here. Yeah. So this is the TensorBoard stuff. That's good. This is a little bit tricky because we're running on Colab, but if you're running on like a Python file, you don't have to say all these. You just need to import the TensorBoard X. So this is the URL that they provided. Currently there is nothing because we haven't started training, but this is a graph classification task. So we are using the IMDb binary graph classification benchmarks. In your homework, I think you're given the enzyme data set, but it's very similar. Load the data set, shuffle the data set, and then start training. The training loop is, remember the training loop is over here. For every epoch, you perform optimization. So yeah, you can also run it. I think it's a little bit slow, but yeah. But let's not waste time. In the meantime, this is the node classification task. So we set task equals to node, so which means that you don't you're actually using the masking for the training and validation split. This is just another data set called CiteSeer, which is also a citation data set, very similar to the Cora data set that's in your homework. But this is node classification. Okay, so this is training. And when it is training, it will start logging, right? So the summary writer is from the TensorBoard X. It will log everything here, log everything that where you say like writer, who is writer? Writer.addScalar will add the scalar to this log directory that you specified here. This is just like very random. Like you can name your log everything, like your favorite name of your model. This is just an example. Like it will log into that directory, and when you log into that directory, this HTML TensorBoard server will retrieve data from that directory, from that log directory, and then you will see a visualization of that. So So this is the name, the random name that we just give our model. We can see the loss function decreasing. So this is for every epoch we're doing this add scalar function there. So we log the add scalar. So we get a plot of this. And note that this is also the test accuracy. But the difference is that at test time, because testing is very expensive, you have to look through the entire data set. We only perform it every 10 epochs. So you will see one data point at every 10 epochs. So note that this is also updating because we are running it and generating log in real time. So this is the TensorBoard. So it's very simple. Like just to reiterate, all you need to do is that you import TensorBoard X, and then you define this writer with the directory that you want to log to, and finally you do where is it? Add scalar, right? It's very simple. And you can also log images and so on, but that's a bit more involved, and I won't talk about it. So lastly, we just want to have a look at the visualization here. So once you learn these kind of node embeddings, no matter from deep work, Node2Vec or GNNs, you can always visualize them in 2D to get a sense like how well your embedding is, like how well the nodes are clustered together. Nodes from the same class are close to each other. You can answer a lot of these kind of questions just by visualizing this. So this is also very simple. This is just using the standard matplotlib stuff that you all probably already know, where XS and YS is the t-SNE embedding here. And the t-SNE embedding is also simple to compute because we have this t-SNE library from SciPy. So we call t-SNE, we construct t-SNE, and then we say fit transform. And then the input to this fit transform function is our embedding that has been learned. So note that this embedding is an output of the model, right? Remember that in our model, where is our model? Remember in our model, we actually output the embedding right here. So it will get the embedding of your graph neural net, and it will perform the t-SNE technique to map this embedding, high-dimensional embedding into 2 dimensions so that you can visualize in this 2D plane by calling plot.scatter with the color representing the class of your each node. So as we can see, like in StatSeer, for instance, it's not perfect, right? There's a lot of nodes that are clustered together. Like in the middle of a brown cluster, there's like red node. So it's not a perfect one. It actually gets like 70% accuracy, so it's not. Yeah.
How do we know if it's an issue with the clustering versus with the classifier?
Oh, the question is how do you know like if you have something wrong, whether it's from the clustering algorithm or whether it's from the classifier? So I think the answer is we gotta trust these low-dimensional embedding techniques. So these are definitely not perfect. The thing is, like, if you imagine you have like a 300 embedding, like 300 dimension embedding, you want to compress it into 2 principal components, or like it's not gonna give you like perfect things, right? So I think it's very hard to determine like whether this is like an artifact or not, especially from this. This is mainly to like show how. This is mainly like show. Why is it disappearing? Never mind. So this is mainly to show like as a comparative study. So say like if you have 2 models, one model gives you this visualization and one model gives you that visualization, and you observe that that model has a better clustering, then given that you use the same t-SNE algorithm, you think that this one is doing better, right? But in absolute scale, it's very hard to determine whether like 2 things are close together. It's really because your method is not good or your t-SNE is not good. But yeah, good question, I think. So that's pretty much the end of the tutorial. And lastly, I just want to show you a little bit about an extra task that is not required in homework. So this is for link prediction, which is also very important. That if you're doing knowledge graph or if you're doing like graph reasoning, it's very important. Basically, it's asking whether you can do completion of knowledge graph or things like that. You can predict whether two nodes are linked together in a graph that has a lot of missing edges, like this kind of cases. So this is just using the graph autoencoder, which you can also refer to the Pytorch geometric documentation. So the encoder, so this kind of autoencoder has this encoder part and decoder part. So the encoder part here, we use graph convolution. We use graph convolution to get embeddings for all the nodes. That's the encoder part. And at the decoder part, we basically use something very simple. We can use inner product, right? If the two embedding have large inner product close to 1, then we think there's likely a link between them. And if they're not, then there's no link. So the encoder is graph conv, the decoder is inner product, right? So here we define a very simple encoder. You're probably already very familiar with this already, like 2 layers of graph conv here. This is your encoder, right? And decoder here, we actually didn't specify because the default decoder is inner product. If you want to have fancy inner product, like fancy things like neural tensor network or any other decoder, then you will modify the decoder also. But overall, it's like just defining another NN.module. So as usual, we do the training test, and we use the site-seer dataset. So this is also the same dataset that we use for node classification, but now we're doing link prediction there. And we're recording these 2 metrics, AUC and average precision, and both of which are also defined in sklearn. So you can use what I said towards the beginning of the class to use sklearn to compute these metrics. So link prediction is also pretty fast. And one thing that's worth noting is that there is the split edges. So this is an important function that helps you to construct positive and negative examples of link prediction. As you probably remember, in class you already talked about like you have to construct positive examples and the negative examples by negative sampling, right? And then you have positive log likelihood minus the sum of log likelihood of your negative samples. So this is doing this separation between the positive edges and negative edges, right? So yeah, this is a good function for link prediction. But other than that, everything is very similar. You define all these parameters and make it to GPU, and then you run over the model. This is the train function that we wrote. So so yeah. And again, we can also visualize this. Color list not defined. I guess I have to run this again just to define the color list. I don't know why it's not defined. But yeah, so the visualization is also very similar. So the idea is that we have an encoder that's graph conv, we have a decoder that's inner product. The thing in the middle is our embedding, so we visualize the embedding in the middle. Yes. I don't know why it's slow, but it's the same function as you saw in the previous node classification thing. And that's it for everything related to Pytorch geometric. And is there any question? Okay, cool. Thanks.
2. Check 1, 2. Check. Hey, Dan. Let's take out the mic. Taking out mic 6. They said the folder says he or she needs like a slide advancer. Do you take one out for them? Do you know? Like a clicker?